So atomic number is Z, that's the number of protons. Mass number is A, and that's the number of protons plus neutrons. So if I subtract Z from A, I should get just the number of neutrons. Okay? Now, the way we write our different elements, or in anything, is like this. So we write the symbol, and on the top is A, the number of protons and neutrons, and on the bottom is Z. Okay? Now we can get Z from the periodic table. So for example, if we were writing helium, it's the second one in the periodic table, the second element, so we would put a 2 here. The number we put up here, though, isn't always obvious. Lots of times the number of neutrons equals the number of protons, so this could be a 4. But in real life, it doesn't have to be. The number of neutrons doesn't have to equal the number of protons, right? There's something that are called isotopes, and I think you've probably heard of them in chemistry. Isotopes are elements like of the same type, but that have the same number of protons, but a different number of neutrons. So helium could be 3,2He. I don't know that I've ever seen a 5, but in theory it could be. Okay, so those are isotopes. So here on your sheet we've written, so there's helium, hydrogen, and there's 3 different isotopes of hydrogen that we'll get to in a minute. We can also write our subatomic particles like this, right? So if you think of an electron, A is the atomic number, A is the mass number, the number of protons and the number of neutrons. Well, an electron doesn't have any of those. And Z is the atomic number, and so we write a -1 there because it's like it has -1 proton. A neutron has 1 neutron for the mass number, so 1, and no protons, so it'll be a 0. And then for a proton, the mass number and the atomic number are both 1, 1. You will often see a proton written like this or with an H11, because really a proton is just the nucleus of a hydrogen atom. Okay? So we tend to write it as a 11P if it's inside the nucleus. But if it's being ejected or emitted, then we write it as a 11H so that it looks like the nucleus of a hydrogen atom. So if a proton's outside the nucleus, it's 11H. If it's inside the nucleus, it's usually 11P. And notice I say usually, so doesn't mean it's always. Before we do nuclear force, let's just hop down since I was already talking about isotopes. So on the back side of your notes, isotopes then are atoms that have the same number of protons but a different number of neutrons, and therefore they have a different mass number. So 3 isotopes of oxygen are 16,8, 17,8, and 18,8. So in this one, it would have 8 neutrons, in this one 9 neutrons, and in this one 10 neutrons. But the number of protons will all be the same. Now usually there's one isotope of the element that's the most common, okay? And there's always one isotope of the element will be radioactive. Sometimes more than one, but always at least one. For hydrogen, there's 3 isotopes of hydrogen, 1,1 hydrogen, which is the most common one, 2,1 hydrogen, and that's called deuterium, and 3,1 hydrogen, tritium. And this one, we make it by artificial means. The tritium, it's radioactive, okay? So it's the radioactive isotope of hydrogen. Now, you can have something like carbon 14,6 and nitrogen 14,7. They have the same mass number. So are they isotopes if they have the same mass number? No. They're only isotopes if they have the same atomic number. So they can have the same mass number but not be the same element. They have to have the same atomic number. All right, going back up to nuclear force for just a minute. Kind of like in quantum, in this unit you will often hear me say the words "we believe" or we think, or at this moment we believe that, meaning we don't know everything about the nucleus yet, just like we don't know everything about where the electrons are. Okay? So we believe there are two forces inside the nucleus. One of these we creatively call the strong nuclear force, and the other one we call the weak nuclear force. And you'll never guess what. Well, maybe you could. We believe the strong nuclear force is much stronger than the weak nuclear force. Doesn't that make a lot of sense? Most of what we know about the strong nuclear force. We know even less about the weak nuclear force than we do about the strong one. So the notes that are written here are really about the strong one. So as far as we know, it's a very, very strong attractive force, but it's short range, meaning it drops off really quickly. Remember our inverse square law for Fg and Fq, right? They were proportional to 1 over r squared. Well, we think that the strong nuclear force is actually 1 over r to the 4th. So what that means is when the r is tiny, like 0.000 whatever, then the F is going to be huge. But as soon as the R starts to get bigger, the F is going to get small really quick. So that's what we mean by short range. It drops off really quickly. This strong attractive force is actually between protons and protons, protons and neutrons and neutrons. But we think it's really only strong when they're about 10 to the negative 15 meters apart. When they get further apart than that, it drops off. It becomes really tiny. Okay, so when they're this close apart, it's actually stronger than the electrostatic force of repulsion. But as soon as it gets bigger than that, then the electrostatic force of repulsion will be bigger than the attractive force, and so it only works inside the nucleus. Okay, it exists, like I said down here, between protons and protons, protons and neutrons, neutrons and neutrons. We think it's about 100 times stronger than the electrostatic force that would be between them, but again, that's only true over small distances. And we also think it's the strongest force known to exist. Of course, not that we know a lot about it. Okay, so we don't have a formula for it yet. That's waiting for you to get out there and get your PhD in nuclear physics and work on it. This is what we know for the moment. You'll notice at the bottom of this sheet that I say read these pages. You probably don't if you've just listened to me. And do these questions 1 to 4. They are the most pathetic questions ever. Okay, they'll take you about 2 seconds if at some point you want to do them. But what I'd like to talk to you about now, where we have some real questions, is we're going to start some nuclear reactions. Okay, now just to understand the whole unit of nuclear, remember we talked about the size of the atom being the size of the classroom, and if it was, then the size of the nucleus would be the size of the tip of this pen. So inside this nucleus are all the protons and neutrons. That's why they're so close together. But remember, the protons don't like each other. So the more protons that are in there, the more unstable the nucleus becomes because they don't like each other. So when we get up into bigger atoms, atoms with more protons and neutrons, but more protons, the nucleus becomes more and more unstable. Okay, it's kind of like having a family reunion where all your aunts and uncles and stuff come, but they don't all get along. And now they're all confined into the house because it's raining cats and dogs outside. It doesn't take very long before the house becomes unstable. And so your grandmother, who's of course overseeing this family reunion, she does what she has to do to make the party more stable, and she throws out the one that she kind of surveys the room and thinks, Uncle Harold has to go. And so she throws Uncle Harold out, waiting to see if the room will become more stable.